So when light goes into a mirror, we found that there is a law. When it hits the mirror and it comes off of the mirror, it's going to bounce off at the same angle that the incoming ray had to the normal. The exiting ray will have that same angle on the other side of the normal. What happens when we hit glass or some clear material? I'm going to take this stacks of plates of glass here and I'm going to put those right into that area. Okay. First thing we're going to notice is, I can see it, maybe you can't, I'm not sure, it's just a very faint light, but here's where that light comes in, right in here. Okay, now if I look on this side, I can see the little red light again. It's right here at the end, I can see just coming out there. I'm going to take this glass out of the way so you can see, and I'll use my little ruler. But it isn't going in the same straight path anymore. And I'll even extend this so you can see it beyond here. It's bent a little bit. As a matter of fact, the normal is still a line we're going to use as a comparison, except instead of bouncing off, it's just going through the material. So if I take the normal here, which is a perpendicular line right through these material, I think you're going to see there's the incoming angle is the angle between the ray and the normal. So let me just draw that in real quick. Here's the incoming ray. Usually we call that theta incoming. The angle of the ray in the middle to the normal is on this side, so that is, if you notice, is a little smaller. So that's theta, and that's a refracted ray. So what do you notice? This is easily, a third bigger again, so that when you're going into thicker media, the field can't respond as fast, the electric field and the magnetic field for light, and so it is slower to respond. We talked about waves travel faster in media that's stiffer, or that the wave can interact with faster. So index of refraction then is for a material how much faster light is in space than it is the media. So it's the media's speed of light versus the speed of light in space. So if it only goes half as fast, the refractive index would be 0.5. If it is 98%, then the fraction is 0.98. So that's the refractive index, and every material has a distinct refractive index. Now, there is no simple rule. It's not the incoming angle equals the exiting angle. It's a little more complex. Snell's law was the person who studied these, has said that it relates back to this index of refraction. So if you took the angle for this incoming one and you took it times the sine and then multiplied by the index of refraction of that medium, so if it's space or even in air, it's pretty close to 1. Then you took the index of refraction of the media you're going into times the sine of that exiting angle, you'd find that those are equivalent. The ends are different, so it will end up becoming different. But here's the general way I want you to remember this, is that an angle coming in from thinner media into thicker, so if you're going into thicker media, the light gets bent towards the normal. If you're leaving thicker media and you're going out, then the light gets bent away from normal. If you can remember those two rules. Into thicker media, you're going to bend towards the normal. Out from thicker media into thinner media bends the light away from normal. That should help us solve several problems as we come up.